So, we will continue our topic which we started in the last class, that is the effect of proportional controller. Fine. And the effect of proportional controller we will observe first for the first order system and then for the second order system. So, initially we will discuss the effect of proportional controller for the first order process. For the first order process, we derived the transfer function G p as K p divided by tau p s plus 1. The transfer function G d equals K d divided by tau p s plus 1. The controller is proportional controller. So, the transfer function of the proportional controller is J c equals K c. The transfer function for the Peon controller can be written as G c equals K c, and for simplicity we are assuming G f and G m both are unity. For simplicity we are assuming the transfer function of measuring device and final control element both are unity. Now, we will try to develop the closed loop transfer function. So, for that purpose we will start from the general form of closed loop transfer function, which can be written as y bar equals G c G p G f divided by 1 plus G c G p G f G m y set point bar plus G d divided by 1 plus G c G p G f G m d bar. Fine. Now, we need to substitute all the individual transfer functions in this generalized form. We need to substitute all the transfer functions, individual transfer functions in this generalized form. If we do that, then we will get y bar equals K p K c divided by tau p s plus 1 plus K p K c y set point bar plus K d divided by tau p s plus 1 plus K p K c d bar. Substituting all individual transfer functions in this generalized closed loop transfer function, we obtain the closed loop transfer function for the first order system in this form. Fine. So, this equation we can write again as K p prime divided by tau p prime s plus 1 y set point bar plus K d prime divided by tau p prime s plus 1 d bar. This form we can write again by this form, where tau p prime equals tau p divided by 1 plus Kp Kc. Kp prime equals Kp Kc divided by 1 plus Kp Kc, and Kd prime equals Kd divided by 1 plus Kp Kc. Fine. Now, what conclusion we can make based on the final form of the closed loop transfer function? Due to the addition of proportional controller, is there any change of order in the overall system? No, there is no change of order due to the inclusion of proportional controller. So, no change of order of the overall system. Fine. Due to the inclusion of proportional action with the first order system, there is no change of order. Second conclusion is tau p prime. Second conclusion can be made based on this: tau p prime less than tau p, and Kp Kc is always positive. Kp Kc is always positive, and therefore, tau p prime is less than tau p. So, what it indicates? Due to the inclusion of proportional action, the overall response becomes faster because time constant is decreased. So, this is the second conclusion. Due to the inclusion of proportional action, the overall response becomes faster. Fine. Now, as I mentioned that the control performance is observed by conducting two tests. One is servo test, another one is regulatory test. So, in the next we will conduct these two tests for the first order process under Peon Lee control. So, first we will discuss the servo problem. First we will discuss the servo problem. Our closed loop transfer function is represented as y prime equals y bar equals Kp prime divided by tau p prime is plus 1 y set point bar plus Kd prime divided by tau p prime is plus 1 d bar. So, for servo problem d bar equals 0, that means the transfer function becomes y bar equals Kp prime divided by tau p prime is plus 1 y set point bar. This is for the case of servo test, because for servo test there is no change in the disturbance, no change in the disturbance is considered. Fine. Now, we will introduce a step change in the set point value, and we will observe the transient behavior of the first order process under Peon Lee control. We will consider a step change in the set point with a magnitude of A. we will consider a step change in the set point value with the magnitude of A, and we will observe the transient behavior of the closed loop process. So, y bar becomes k p prime divided by tau p prime s plus 1 multiplied by A by s, agree. By considering this set point change in, by considering the step change in set point value, we get this form. Now, if we take the inverse of Laplace transform, we get y t is equal to k p prime A 1 minus exponential of minus t divided by tau p prime. Taking inverse of Laplace transform, we get this form of y in time domain. Fine. Now, we will try to discuss the offset. I mean, we will try to determine whether the process under Peon Lee controller shows any offset or not. Offset. Offset is calculated by representing as new set point minus ultimate value of the response. Offset is calculated using this form, new set point minus ultimate value of the response. Now, ultimate value of the response means limit t tends to infinity y t. Ultimate value is calculated by using the final value theorem, that is limit t tends to infinity y t, or we can represent in Laplace domain also by limit s tends to 0 s multiplied by y bar s. Fine. Ultimate value of the response is calculated by using this form, by using final value theorem. So, what is the ultimate value of the response for this case? Set point value is A. Set point value is A because we have introduced a step change with magnitude A, and what is the ultimate value? K p prime A. If we apply the final value theorem, we can obtain the ultimate value as k p prime A. Now, offset becomes A multiplied by 1 minus k p prime. Substituting the expression of k p prime, finally we get A divided by 1 plus k p k c. Fine. Offset is calculated by using this form, new set point minus ultimate value. Here set point is A, ultimate value is k p prime A. Substituting the expression of k p prime, finally we get the offset equals A divided by 1 plus k p k c. So, if we produce the plot, in terms of transient response, and y set point t. Now, we are introducing step change in y set point. So, initially it was 0. Now, we are giving a change in y set point. This is A at time t equals 0. Fine. Now, the process under P only control responds like this. This is the process response under P only control y, and this is representing y set point. Fine. This plot represents the process behavior under P only control scheme, and also by introducing step change in set point value with a magnitude of A. Now, this deviation, steady state deviation of the control variable from set point value is offset. This difference is offset, and mathematically it is A divided by 1 plus kpkc. Mathematically we obtain offset equals A divided by 1 plus kpkc. Fine. Now, when kc tends to infinity, what about offset? We got offset equals 1 divided by 1 plus kpkc. Offset equals A divided by 1 plus kpkc. Now, when kc tends to infinity, offset approaches 0. When kc tends to infinity, when kc approaches infinity, offset approaches 0. But we discussed in the last class that there is a maximum limit of kc beyond which the process goes unstable. So, we cannot arbitrarily select a large value of kc. Fine. So, kc tends to infinity, this cannot be considered in practice due to some maximum limit of kc value. Next, we will consider the regulatory test. Next, we will discuss the regulatory problem. So, our closed loop transfer function for the first order system under P only control is Kp prime divided by tau p prime s plus 1 y set point bar plus Kd prime tau p prime s plus 1 d bar. This is the closed loop transfer function for the first order system under P only control. Now, for the regulatory problem, there is no change of y set point occurred. No change in the y set point is considered. So, for the regulatory problem, the closed loop transfer function becomes y set point equals Kd prime divided by tau p prime s plus 1 d bar. This is the closed loop transfer function for regulatory test where no change in y set point is considered. Similarly, we will consider a step change in the disturbance with a magnitude of A. Considering a step change in the disturbance with a magnitude of A, we get the closed loop transfer function as y bar equals k d prime divided by tau p prime s plus 1 multiplied by A by S. Fine. Taking inverse of Laplace transform, we get the process output y in time domain as y t equals k d prime A multiplied by 1 minus exponential of minus t divided by tau p prime. Taking inverse of Laplace transform, we obtain the y in time domain by this. Fine. Now, we will try to determine the offset. Offset equals new set point minus ultimate value of the response. Ultimate value of the response. The ultimate value of the response can be determined by the application of final value theorem. Anyway, how much is the set point? Set point is 0. And how much is the ultimate value of the response? K d prime A. Ultimate value of the response is k d prime A. Substituting the expression of k d prime, we obtain offset equals k d A divided by 1 plus k p k c. Substituting the expression of k d prime, we finally get the offset equals minus k d A divided by 1 plus k p k c. Now, we will produce a plot to observe the transient behavior. We did not consider any change in y set point. So, y set point remains constant throughout the operation, but we have introduced a step change in the disturbance at time t equals 0. So, the process output changes from t equals 0. This is the process output under P control. And if there is no control, then the process response behaves like this. Fine. We did not introduce any change in the set point, therefore, the set point remains constant throughout the operation, but the disturbance is changed at time t equals 0. Therefore, the process changes to a different steady state value starting from time t equals 0. And if there is no controller, then the process responds like this. Now, this is the steady state error. That means, this is the offset, which is equal to minus k d A divided by 1 plus k p k c. Fine. Now, if you see the expression of offset, again we can say that when k c approaches infinity, the offset approaches 0. If we see the expression of the offset in the regulatory test, we can say that if Kc approaches infinity, the offset approaches 0. Now, we will conclude. So, if we see the expression of tau p prime, we can say that the tau p prime is less than tau p. Fine. If we see from this expression, we can say that tau p prime is less than tau p. So, due to the inclusion of proportional controller, the overall response becomes faster. Another observation is with the increase of Kc, the tau p prime decreases. With the increase of Kc value, tau p prime decreases. So, if you recall this plot, which includes the process response under different Kc value. This is Kc2. So, here Kc1 is greater than Kc2. Fine. Now, if Kc1 is higher, then the process under Kc1 reaches the steady state quickly than Kc2. That we need to include also in this figure. Secondly, we can say that the process under P only controller shows offset. That means, it is proved that the P only controller cannot eliminate offset. Fine. So, next we will discuss the P only control of an integrating process. P only control of an integrating process. Next we will discuss this. So, for this purpose we need to consider an integrating process. This is a liquid tank. Two input streams are involved in this example. One is F1, another one is F2. One outlet stream is involved, which has the flow rate of F naught, and one constant displacement pump is installed in the outlet section. This is a constant displacement pump. it indicates f naught is a constant term, fine, f naught is constant. Now, in this particular example, we can say that the control variable is liquid height. Suppose the manipulated variable is f1. So, load variable will be f2, fine. If we consider f1 as the manipulated variable, then f2 is the load variable. Now, we will develop the transfer functions of the different elements. So, first is the process. Performing mass balance, we can write A dH dt equals f1 plus f2. Performing mass balance, we can write for the example system as A dH dt equals f1 plus f2. All these variables are represented, all these variables are here deviation variables. So, this equation is written in terms of deviation variables, and therefore, there is no f naught term, fine. So, to represent the deviation variable, we are not using superscript prime. Now, if we take Laplace transform and if we rearrange, then we get h bar s equals 1 divided by f s f1 bar s plus 1 divided by f a s f2 bar s. Taking Laplace transform, we get this form. So, from this form, we get the transfer function of the process G p with respect to m as 1 by A s and G d s is also equal to 1 by A s, fine. From this equation, we get the transfer function G p and G d s, and both are equal to 1 by A s. So, next element is the controller. Our controller is the P only controller. So, the transfer function of P only controller is G c equals K c. This is the transfer function of P only controller. Now, for measuring device and final control element, we will consider both the transfer functions as unity. The transfer function of measuring device G m and final control element G f are unity. Now, we will try to develop the closed loop transfer function for the example system. The generalized form is y bar equals G c G p G f divided by 1 plus G c G p G f G m y set point bar plus G d divided by 1 plus G c G p G f G m d bar. This is the generalized form of closed loop transfer function. Now, if we substitute the form of individual transfer function, then we get H bar S equals 1 divided by A by K C S plus 1 H set point bar S plus 1 divided by K C A divided by K C S plus 1 F2 bar S. Substituting the expressions of individual transfer functions in the closed loop transfer function, we get this form. Fine. Now, we will conduct the servo and regulatory tests to observe the closed loop process behavior. So, first we will consider the servo test. First we will consider the servo test. So, this is servo problem. So, for servo problem we can write that F2 bar S equals 0, because there is no change of disturbance. Accordingly, the closed loop transfer function becomes H bar S equals 1 divided by A by K C S plus 1 H set point bar S. This is for the servo test. Considering F2 bar equals 0, we get this closed loop transfer function for servo problem. Now, we will consider a unit step change in the set point value of set point of H. That means H set point bar S equals 1 by S. So, considering a unit step change in HSP, we get the transfer function as H bar S equals 1 divided by A by K C S plus 1 multiplied by 1 by S. Fine. So, what will be the offset? Offset we can calculate by finding the new set point minus ultimate value of the response. What is new set point? 1. What is ultimate value? Ultimate value we can find by the application of final value theorem, that is also 1. So, offset becomes 0. Fine. So, it is very interesting that for an integrating process, the P-only controller provides offset free response. It is very interesting that the P-only controller provides for an integrating process offset free response. Definitely, by conducting the servo test we got offset equals 0, but we need to also conduct the regulatory test. So, in the next we will conduct the regulatory test and we will see what is the offset. Our transfer function, closed loop transfer function is h bar s equals 1 by k c divided by a by k c s plus 1 f 2 bar s. This is the closed loop transfer function for the integrating system when there is no change is introduced in the set point. So, this is for the regulatory case. Fine. Introducing a unit step change in F2S, we obtain h bar s equals 1 by k c whole divided by a by k c s plus 1 multiplied by 1 by s. Introducing a unit step change in F2, we obtain the closed loop transfer function in this form. Can you calculate now the offset? The offset will be calculated by finding the new set point minus ultimate value of the response. So, new set point is 0 and ultimate value is minus 1 by k c. So, this is equal to minus 1 by k c. So, for the regulatory problem we obtain non-zero offset. Fine. But it is important to note that usually we are not interested in maintaining the liquid level system at the desired value, but within a certain range. We are not interested in maintaining the liquid level exactly at the desired value, but at a certain range. In that sense, we can say that the Peon controller is sufficient to control the liquid level system. Fine. The Peon controller is sufficient to maintain the liquid level system. Another important thing is that if Kc is quite large, then this offset is acceptable. If Kc is large, then the offset represented by minus 1 by Kc is acceptable. So, Peon controller can be used to maintain the liquid level system. So, this is all about the effect of proportional control on the first order system. Similarly, we will observe the effect of Peon control on the second order system. So, next we will discuss second order systems under Peon control. Next we will discuss the dynamics of second order system under Peon control, and here we will only consider the servo problem. Here we will consider only the Servo problem. Fine. The first element of the closed loop process is the process, I mean the open loop process. The transfer function of a second order process has this form: GPS equals y bar s divided by m bar s equals Kp divided by tau square a square plus 2 zeta tau s plus 1. This is the transfer function of a second order process. Next element is the controller, and the controller is P only controller. So, the transfer function can be written as Gc equals Kc. This is the transfer function of P only controller. Final control element and measuring device. For final control element and measuring device, we will consider the transfer functions equal unity. So, the transfer function of final control element and measuring device are unity. Now, we will write the closed loop transfer function for the second order system under P only control. Substituting all these individual transfer functions in the generalized form of closed loop transfer function, we obtain y bar equals Gp Kc divided by 1 plus Gp Kc y set point bar plus Gd divided by 1 plus Gp Kc d bar. Substituting all the transfer functions except the process transfer function, we obtain this form. Now, we will consider only the servo test. We will only conduct the servo test. So, for the servo case, the transfer function yields y prime equals Kc Kp divided by tau square a square plus 2 zeta tau s plus 1 divided by 1 plus Kc Kp divided by tau square a square plus 2 zeta tau s plus 1. Fine. Substituting the transfer function of the open loop process, we obtain this expression. Now, we can represent this transfer function as y prime equals Kp prime divided by tau prime square a square plus 2 zeta prime tau prime s plus 1 y set point bar. Yeah, here we need to multiply y set point. Now, Kp prime has the form of Kp prime equals Kp Kc divided by 1 plus Kp Kc. Similarly, tau prime has the form of tau prime equals tau divided by root over of 1 plus Kp Kc, and zeta prime equals zeta divided by root over of 1 plus Kp Kc. Fine. So, due to the inclusion of P only controller with the second order process, there is no change of order. So, first observation is that due to the inclusion of P only controller with the second order process, there is no change of order in the overall system. Another observation we can note, that is tau prime less than tau. If we see the expression of tau prime, we can say that tau prime less than tau. Similarly, zeta prime less than zeta. Similarly, if we see the expression of zeta prime, we can say that zeta prime less than zeta. That means, under P only control we may obtain oscillatory response. I mean, the overdamped system may change to underdamped system under P only control. Fine. Okay, thank you.